Symbolic execution has its challenges, from path explosion to complex constraints. Addressing these challenges is what made symbolic execution so popular today. It is used for test case generation, debugging, and verification. What you see here is a static analysis engineered to improve the performance of dynamic symbolic execution, which leads to the most epic of results.
In 2013, we put 140 students on a single project, and it worked. Now we're taking our course out to the world, and we'd like you to help. If we're going to teach the inherently collaborative nature of programming, we should do it collaboratively. We're hoping this can become a place where the computing community teaches students to program together. Are you super collaborative? Because with your help, we are.
Good morning.
Right?
Wrong. Don't do that.
Herding cats. Don't let anybody tell you it's easy. Good morning, everybody. My name is David Rosenblum. I'm from the National University of Singapore, and it's my pleasure this morning to present the ICSE Most Influential Paper Award. The ICSE MIP Award, as it's usually called, is awarded to a research paper from the ICSE that took place 10 years ago, in this case ICSE 2004, which took place in Edinburgh, Scotland. And the award recognizes the paper that has had the greatest influence on the research activity and research directions of our field. I was one of the program co-chairs for ICSE 2004, along with Jackie Estoublier, who unfortunately wasn't able to attend the conference this year. And the two of us were asked by Pankaj to lead the selection of the paper that would end up receiving this award. As we set about our work, we realized that our work was going to be very easy because there was one paper that clearly stood out from all of the other papers that had been presented that year, despite the fact that there were many fine papers that were presented at the conference in Edinburgh. The paper we ended up selecting stood out not just because of the high number of citations it's gained over the last 10 years, but also because of the very strong influence that it's had on the kinds of research that people in our community are doing nowadays. The paper that was selected is the paper Mining Version Histories to Guide Software Changes by the authors Tom Zimmerman, Peter Weisgerber, Stefan Diehl, and Andreas Zeller. This paper was an early milestone in the application of data analytics to large software repositories for the purpose of gleaning insights, deep insights about some software development project and about software development itself in general. And it helped lead to the establishment of mining software repositories as a very important and active line of research in our community, and the authors of this paper remain leaders in that area to this day. So without further ado, it's my pleasure to invite three of the authors who are here at the conference, Tom, Stefan, and Andreas, to come up and receive the award and to spend a few minutes sharing their insights about their paper and the influence that it's had on the field. So first of all, let's congratulate these authors on this award.
I can take photos.
Okay. Congratulations to all three of you. Please go ahead.
Mikrofon. Ich glaube, du musst hier rein.
Good morning, everyone. Interestingly, our work was rooted not in the software engineering community, let's say, but it actually started all in craft drawing. In the late 90s, I was working at the compiler design chair at Saarbrücken University, and I actually was doing a project where the goal was to visualize the generation of finite automata. We were looking in the literature for an algorithm to draw these automata, but we couldn't find an appropriate algorithm. So we actually developed the first algorithm for drawing dynamic graphs offline. The problem is that you have a given sequence of graphs, and you want to draw them in a way that the mental map of the user is preserved. So at that time, everything looked like a graph to me. And I had the initial project idea that given a sequence of program graphs, I wanted to identify and visualize recurring patterns in this sequence. So I wrote a project proposal, but it was rejected. At about the same time, Andreas began to work at Saarbrücken, and I knew that he had experience in configuration management. So I went to him to discuss my idea. So on the slide, you can see an original note from our meeting. Andreas contributed his knowledge about version archives to the project idea. As a coincidence, just 2 weeks before our meeting, he had listened to a talk by Rakesh Agrawal about data mining. So we had the missing puzzle piece that we could use data mining to find these recurring patterns. We wrote a project proposal, and the proposal got accepted, and we got funding. Luckily, we had 2 hungry as well as talented students, Tom Zimmermann, who is now working with Microsoft Research, and Peter Weisgerber, who is now working with Amazon Europe. Peter, unfortunately, cannot be here today. We started our work with extracting data and analyzing data from CVS archives. On this slide, you can see a matrix showing the evolutionary coupling of the data display debugger software. Evolutionary coupling is also called co-change coupling by some authors. In this example, you can see that, for example, you can see that patches and tests are typically changed together with the source code. Red pixels on these, in this matrix show strong coupling. We published our first results at IWPSE in 2003 at Helsinki. We were interested or investigating whether the evolutionary coupling would match with the hierarchical module structure of a system. We argued that if red blocks of red pixels would appear along the diagonal of this kind of visualization, this would indicate that the architecture of the software would be good, because it would indicate that changes are confined within the boundaries of a module. Thank you.
So this was the paper that actually came out of it, and for us this was the opportunity to get in touch with the then emerging community of automated empirical software engineering. But what we also found was that at the time, these early approaches in looking into version histories, and this was done only by a handful of people, were still in the sense of traditional empirical software engineering. That is, you make a study, you write a nice paper about it with nice visualizations, a couple of metrics, and show that the metrics work. But with us coming from program analysis, we had the developer in mind, and we wanted to support developers in their daily work. So we wanted to make these results actionable. And just to give you an idea of how we thought that this could be useful, I am a developer. I am working here in Eclipse, on the Eclipse source code, and I'm entering some code that would add a new preference to Eclipse. And I'm entering this right away. Now I'm done. And the question is this the only place where I'm adding a preference? Is there anything else I would have to change somewhere? And this is, of course, a not so easy question, because Eclipse consists of, at the time, it was 47,000 files, and it's not always easy to find out where you need to do something. And that's when, that's when the idea of data mining and the main application of data mining came to us. The main application of data mining is to make recommendations. Recommendations as in ads, but also recommendations when you're buying something, such as this very fine book on recommendation systems, for instance. You buy something at a site like Amazon, and data mining tells you, well, people who bought this item also bought, or people who viewed this item also viewed other items. So to make other recommendations of other items to you. And this was the idea we wanted to apply to software development. You change something, and people who changed this item also changed these other items. And in order to do this, we built an appropriate mining tool. And when I say we built an appropriate mining tool, that was something that took us several months to build because nobody had ever done this before, or for automated purposes. And from such a mining tool, we could then extract individual sequences of changes. For instance, we could find out that on the 19th of February, a developer would change the following 7 items, as listed here on the slide. However, it turned out that these 7 items were frequently changed together. So what you could find is not that there were overall there was a total of 9 individual transactions in the history of Eclipse, where here fkeys, the fkeys array, and the init defaults function were changed together, and in 8 of these, the file plugin properties was changed as well. And data mining, standard data mining algorithms would now be able to extract rules such that whenever people changed fkeys and init defaults, they typically would also change plugin properties. And standard data mining algorithms would take an entire data set and give you all rules, but this would take several hours. So we set up a new, well, we invented a new variant that would take a couple of known antecedents and deduce the consequent, that is the other files to be changed in less than a second. This was something that we could then implement as a plugin to Eclipse. And I'm here in the same session that I previously left, so I just changed something. Now I'm going to save the file. And as I save the file, our eRows plugin would automatically show here at the bottom of the screen, would automatically show other locations that I should be investigating, because these also would have been changed in the past at the same time. If you look closely at the list of recommendations over here, you will find that the first one is a Java file, but the next one is a text file, and the other one is an HTML file. And this, for us, again, as we came from program analysis, was something that we found very exciting. Finding links between program files, or finding links within programs, is something we had been doing all day long. But being able to connect a location in a program to a preference file, which would exactly, where the thing we changed in the program would be exactly connected to a specific location in that preference file, was something entirely new. And also be able to create links between program files and, in this case, build nodes, for instance, an HTML document. This was something that no program analysis technique at the time would ever be able to uncover. And we would uncover such links, and we would uncover such links from history. So that was the great news. We evaluated the whole approach, and since we were pretty new to empirical software engineering, we decided to play it safe, and we made it a rather big evaluation with a total of 8 projects, big projects. So we didn't spare effort here. It was actually one of the largest studies at the time, given the number of lines of code that we analyzed here. And for these projects, we would go and check how good our recommendations were. How good were our recommendations? Well, again, from the perspective of program analysis, are actually pretty poor. If you look at the top, if we looked at the top recommendation, only 26% of them, in terms of functions, would actually be correct. And in terms of files, which would be a wider range, only 30% would be correct. But then we thought, well, in the end, this is not program analysis. We're not looking, we're looking at the same precision here. We know this is more like a Google search. You search something at Google, and no, it's not always the case that the first recommendation is the right place, but maybe it's the top 3, or maybe it's in the top 10. And when we looked at the top 10, whether these would contain a correct recommendation, yes, this would be the case for 90%, and even for the top 3, which was our standard measure, it was 70%. So with that, we sent out our paper to ICSE 2004, and several months later, we would get back the reviews. And the reviews were, well, the reviews were not something that would give us hope that we would stand on that stage 10 years later. Quoting from the first review, the authors have written a very smooth paper, a very clever idea, a very nice evaluation, but. And if you ever got an ICSE review, you know what a but means at this point. Okay, you started with something nice, the authors have written an interesting paper, but. Okay, the paper is well written, but. The research is okay, but. Okay, so, good. And then came the blows. 3 reviewers out of 4 said the results are not very good. Again, from the there were no similar systems to compare against, and the idea of having systems with a number of false positives was simply pretty new to the community still, and that's what essentially all reviewers stated to us, and. This was the most difficult paper this reviewer had in her stack. Hey, if you're into identifying reviewers, we now know the gender of that reviewer. But we really must praise the program committee for going way out of their comfort zone and still accepting the paper, despite it being very smooth and very clever and whatnot, what they said, and despite the results that left room for improvement. And the paper eventually got accepted, so that was fine, and that's why we're here on the stage today. But while we're here on the stage, we cannot be here without also mentioning and praising the others that went in the same direction as we did. Independently from us, there were at least 2 groups that were working in a very similar direction. One is Annie Ying, who in her master's thesis went and did a very similar work in predicting code changes from earlier changes. And the only thing that held her back from submitting to ICSE was that she was not yet satisfied with the results and decided to wait for another couple of months. So we were slightly ahead of her. And the other one was Ahmed Hassan, who in his PhD thesis also had investigated the propagation of changes. And all of these 3 works share the similar goals and go along with very similar results. And any of these with a little twist of history could also be here on the stage today. And with that, I hand over to Tom.
And so what was really exciting at the time is that so we had just begun looking at data, so we looked at version archives in this work, but actually there was lots of data just waiting to be analyzed, and that's what the community actually picked up on very quickly. So it was like being a kid in a candy store, and there's so much different type of data that you could look at. Like in the beginning, people were looking at bugs, changes, emails, communication in general. Over time, when platforms like Stack Overflow, GitHub emerged, and all this was like data that the research community started mining and generating insights for the community. And more recently, more exotic types of data are being looked at, like app stores, energy, code reviews are also very hot at the moment, and also usage data about how the how the customer is using a software. And at that time, like the main venue and like what significantly contributed to the growth of mining software repositories as a discipline was the Mining Software Repositories Conference, which was founded by Ahmed Hassan, Rick Holt, and Audis Mockers in 2004, so at the same time as our paper was published. And mining software repositories, it's actually very exciting. So it helped me in my career a lot to grow and to make important connections. And since 2004, the MSR conference has published over 400 papers with over 250 different authors. And it actually grew from a workshop in 2004 to a conference, which is now actually the largest co-located event with ICSE, with more than 150 people every year. And it also, what's great about the MSR conference is it actually has several venues to advance the field of data analysis, like the MSR conference has the data showcase track, where people essentially can share the data to the academic community and they get as credit a publication out of it. Or the mining challenge, in which young PhD students essentially get exposed to the field of mining software repositories. What I always found very fascinating is that all of us who were in mining software repositories actually were way ahead of the curve. And that's what we're showing on this slide over here. Essentially, it's showing you the number of searches on Google for keywords like data science, big data, data analytics, which are like very hot topics. Like to everyone, when you talk to companies, they're like very excited about it. But if you look at the chart, essentially the Google search interest more or less only started in like 2010, 2011, but the mining software repositories research essentially all started in 2004. And there were many people working on it. So that's very exciting because we were ahead of the crowd. And it's not just that mining software repositories was an academic thing. Actually, there's been a lot of impact in the industry, like companies like Google, SAP, IBM, and also Microsoft have been doing a lot of work in mining software repositories. And what you can see on this slide here is some of the examples of the work we've done at Microsoft Research. So on the left, you can see the infrastructure that we have to collect all the data from software repositories to put into like a huge data mart, on top of which you can build different applications, which you could see on the right-hand side. So I briefly want to mention a few directions for the field where I think we're heading in the future. I think the first one it's a bit obvious, but it's actually there's still lots of data waiting to be analyzed. So one future direction is we're going to see more data analysis, different type of data, because in the end, data is not going away. But as it is with candy, if you eat too much, you'll get sick. So really one thing that is going to be important for us as a community is to start thinking about how we can make data analysis more healthy. So not just eating candy, but also how can we advance our methods, do more, essentially improve the insight that we're generating by looking at data. Next is, I think, it's going to be mining for everyone. What we started as an academic community has grown throughout the field, and it's now more prevalent in industry, and there's a lot of interest. And what I think will happen is that in 10 years from now, every software engineer will have some basic understanding on how to look at their own software data, how to improve the work and the software that they produce. And because of that, it's going to be very important for us to think of ways how we teach future software engineers to look at data. So with this, I want to say that we are very proud to be part of the mining software repositories community, which is very vibrant, productive, and creative. And if you want to experience this, just go to the Mining Software Repositories Conference or listen to any of the Mining Software Repositories papers at the conference or at any other conference. And we look forward to much to much more impact of mining software repositories in the future. So thank you very much for being here, and thank you very much for the award. Thank you.
So good morning. So now it's time for the second keynote of the conference. It is our distinct pleasure to welcome Charles Lee Isbell this morning. He is a senior associate dean and professor at the College of Computing, Georgia Tech in Atlanta, and more specifically the School of Interactive Computing. After completing a Bachelor in Computer Science at Georgia Tech and a PhD at MIT in 1998, he went to work for NTNT Labs, the research labs, and eventually returned as a faculty member to Georgia Tech. Charles' passion is artificial intelligence, and he is currently focusing on applying statistical machine learning to building autonomous agents. And more specifically, he has been currently focusing on adaptive modeling, scalable coordination, and development environment to support the rapid prototyping of adaptive agents with various applications in software engineering and programming languages. So without further ado, Charles, the floor is yours.
At least I hope I have it. Let's see. We appear to have disconnected my computer. So bear with me, if you will, for just a moment. Yeah, I'm not connected. Yeah, that looks right. There we go. Excellent. Okay, so good morning, everyone. It is a great honor to be here, and I appreciate you inviting me. Like many of you, I had a fairly difficult time getting here. I got my visa about 3 hours before my flight took off, but I managed to just catch the airplane and get here, and I'm very happy. I enjoyed yesterday. I enjoyed the talks that I had a chance to hear. So the reason I'm here today is to talk to you a little bit about the Online Masters of Computer Science, which is a new program at Georgia Tech. I'll give you a few details about that in a moment. But what I want to sort of get across here are a few important things about the degree program and its possible impact for computer science and for computing broadly. I'm a professor. I'm also the Senior Associate Dean for the College of Computing, and so I sort of spend most of my days dealing with the balance between those things. So what I'm going to try to encourage you to do today is to ask me questions. I'm going to try to keep the talk relatively short and not use my full hour so that you can ask me what you want. And the way that I'm going to do that is I'm going to do two things. One, I'm going to make a lot of absolute statements with complete and total confidence, thus proving to you that I am in fact a professor. But at the same time, I'm also going to hold back some of the details that might prove embarrassing to me and my colleagues, thus forcing you to ask me questions if you want to understand what really happened and how we really got here, thus proving to you that I am, in fact, an administrator as well. Okay? So this is a bit of an experiment, and I'm hoping to encourage questions towards the end, and you should feel free to ask me anything that you want about both this program and what I think the implications are for our field. So what am I going to talk about? I'm going to talk about the OMSCS. So many of you will have heard about this, but for those of you who have not, let me share a few details. The important thing going on here is that we're taking the MOOC platform, in particular one from Udacity, which I'll talk about in a little bit, and we're trying to apply it to the notion of an entire degree program. So for the last couple of years, and it's only been a couple of years since we started going down this particular track, we have been applying this notion of broad education to courses, sort of individually one at a time, maybe 3 or 4 courses together. But the goal here was to figure out how could we take that notion of broad dissemination of education in individual courses and build an entire degree program out of it. Now, I also want to point out that this degree program that we have developed is not simply a degree program that we threw together. It is the equivalent of our Masters of Science in Computer Science. In fact, there is no distinction whatsoever on the transcript or on the diploma. If you go through this program and receive this Masters of Science, you receive the same Master of Science in Computer Science as the tens of thousands of people over the last decade who've taken our Masters of Science on campus. In fact, although I will refer to it as the OMS sometimes, and we talk about it that way in our literature, there is no distinction as far as the state of Georgia is concerned or as far as Georgia Tech is concerned. The other thing that's important here, I think, is we really wanted to take seriously this notion that this technology might help us to provide education not just more broadly, but more affordably. So the entire cost of this degree program is $6,600 US. This is by comparison to roughly somewhere between $42,000 and $50,000 if you're an out-of-state student taking the degree program on campus. I'm going to talk a little bit about how we came to $6,600 and sort of how this entire evolution went. But the main idea here is that I want to get across to you that this sort of technology and this approach has the potential to radically change and democratize education, certainly at the level of a master's program or above, and to bring professional degrees to people all over the world. So that's a relatively strong claim, and I'm hoping to back it up over the next few minutes. So let me give you a little bit of context, which will help to explain both the technology, or both the sort of technical content of the master's program, but also some of the implicit politics that are involved in developing such a thing. The first thing you have to understand is that this is a program that was developed at Georgia Tech. Now, Georgia Tech has 6 colleges. Its largest is engineering. In fact, Georgia Tech is the largest engineering college in the United States. It produces more engineers, more black engineers, more Hispanic engineers, more female engineers, more engineers, period, than any other university in the United States. But it has a separate college of computing that's been around as of next year for 25 years that did not come out of engineering, but came out of something that was once called sciences a couple of decades ago. It is because we are a separate college of computing that we're able to develop this without having to deal with this sort of implicit politics of being at an engineering college, and it made a relatively large difference in our ability to be flexible with our own degree programs. Now, in addition to the 6 colleges at Georgia Tech, there is a college, it's not really a college, it's an academic unit of professional education. So like many of you out there who are part of various universities, Georgia Tech has been in the game of distance education in one form or another for the last 3 decades. This, however, represents something new, but because we had this experience, we were able to take all of that, the things that we knew that worked and the things that we knew that didn't work, and apply them to this new approach. So the last little bit of context before I get into the meat of it is that our master's program is 36 credit hours. That works out to be roughly 12 classes. It takes most students anywhere between 18 months and 24 months going full-time in order to get through this program. We have 2 options, 3 options. So in addition to the course-only option, we have a project option and a thesis option, which takes away some of the hours. We are focusing here only on the purely class option. There are 15 specializations ranging from architecture to scientific computing and AI and machine learning and everything in between. So we have a relatively complicated degree program. It reflects most of the degree programs at Georgia Tech. We have 8 graduate programs, all but 2 of which are across multiple departments and many of which are across multiple colleges. This happens to be the one that lives entirely inside the College of Computing. So with that little background, let me dive into what we were trying to do and why I think it might be important. So the first question that I get asked when I talk to people about this is, why did you try to create a MOOC-delivered Masters of Science in Computer Science? I'm going to go through a couple of slides and go through a lot of detailed answers for that, but basically it's a very short answer. It's because we can and because we should. The first part is important. The technology has reached a point where we can actually provide connections to people all over the world in real time to allow them to educate themselves. That's relatively new. We've had many of the pieces, but they've all sort of come together in the last 5 or 10 years. But more importantly than because we can, we should. There are lots of opportunities here. There are lots of options for people who would like to get further education, are capable of getting further education, but simply do not have the time, the means, or the finances. And the goal here was to figure out how we could make that work while still maintaining the level of quality that we expect in a top 10 Masters of Science program. So here's some of that spelled out a little bit more. How can we? Well, the idea is that now's the right time for this effort. I think I don't have to tell most of the people in this audience that we have rapidly maturing technology. I mean that both in terms of hardware and in terms of software. We have a lot of experience. We have 20 plus years of doing long distance education, actually about 30 years. Many of the people here in the audience have done things of this sort. We've been spending the last two or 3 years, depending upon how you count, doing MOOC-based education. We sort of know what works and what doesn't work. At Georgia Tech, we've had at this point, 30-something courses that are out there available on Coursera, Udacity, and various other platforms, and we have just quite a bit of experience for sort of what kinds of things make sense and what sort of things don't make sense. At the same time, the rest of the world seems to be interested. I don't have to tell you about the hype that surrounds MOOCs, that surrounds Coursera, Udacity, and edX, because it's in the Chronicles of Higher Education and at the front of the New York Times and the Wall Street Journal. And that means that philanthropic entities, the Gates Foundation, various other organizations like this are interested in figuring out how to put money into this to make something that's useful. But just as importantly as have the technology being ready, we think that computer science in particular, and a Master's of Science in particular, is a nice, safe place to start running the set of experiments you would need to run to know whether something like this is actually feasible at the end of the day. And so we decided dive in feet first, figure out what's going on, and see what we can do to create such a program. So, in addition to the fact that we can do this, I want to spend just a moment explaining why we should. Perhaps I don't have to convince you, but I actually think it's important to take a moment to reflect upon the potential that is in front of us today. Georgia Tech, being a state public institution, has a motto, progress and service. It is a part of our mission to understand how to educate people in Georgia, in the United States, and across the world, and this is something that we take relatively seriously. It also turns out that in our own studies and interacting with students and being students ourselves, we understand that students want certification, not just exposure. And it's not just that they want exposure, they want degrees. They want something that they can take with them and get a job at Microsoft Research or Intel or Google or anywhere else where they might want to work. We have the technology, we have the experience, and we have here something that, at least for me and for many of the other people that participated, including people who are in the audience today, an actual opportunity to redefine education and student-focused education through this technology. If we can figure out how to take something like a MOOC, something like a degree program, and make it work with 5,000, 10,000, 50,000 people, then we have an opportunity to have a huge impact. Now, there's more to it than that, of course. There are lots of selfish reasons to do this. From Georgia Tech's point of view, from the Institute's point of view, and from the faculty's point of view, this is an opportunity to reach students we have not been able to reach before. Both students who are good, who simply couldn't come, and also students that we aren't sure would be PhD quality, but we would love to take a relatively low risk in interacting with. And this sort of gives us the ability to do that. There's a last thing that sort of motivates a lot of us, and I think that it's worth taking a moment to mention that as well, and that is this notion of where prestige comes from. So a couple of months ago, there was a bunch of newspaper articles splashing all over, at least in the United States, talking about the acceptance rates at the Ivy Leagues. So places like Stanford, Harvard, are now gotten down to not only single-digit acceptance rates, but down below 5%. So most of the prestige that a university gets comes from its ability to say no. We're only going to accept 5% of our applicants. Which is sort of an odd thing if you think about it for a moment, right? A good university is a university whose outputs aren't much worse than its inputs, right? That does the minimal sort of damage to its students. And what you would like to be able to do is to change this notion of saying no to all the students you aren't 100% sure about, and instead be able to give all the students who have an opportunity a chance to go through your university, go through your programs, and then come out great at the other end. So here what we're trying to move from is not we're only going to accept 10% of the people who apply to our master's programs, but we're going to accept 100% of all the qualified students. They're going to go through our program, they're going to get master's degrees that are just as good as and perhaps even better than the master's degrees for their on-campus counterparts, and they're going to be able to go out in the world and prove that a Georgia Tech education is an exceptional one. That seems like a small thing, I think, but it's actually a gigantic thing. This idea of completely rethinking why we're doing education as a business enterprise as well as an educational one, and to bring those two closer in alignment. So why Udacity? So this program is not simply something that we did at Georgia Tech. We had to partner with two entities to make it happen. One is Udacity, which is one of the three big MOOC providers, along with Coursera and edX, and AT&T, who provided us with a $2 million startup gift. We decided to go with Udacity for a couple of reasons. One very simple one is that Sebastian Thrun, who's one of the founders of Udacity, came to us with the idea of creating a $1,000 Master's of Science degree. We talked to him about it. We thought $1,000 was probably a little too low, but that it was a great idea and that we should try to figure it out. So the right thing to do was to work with them. But more importantly, it turned out that a lot of their interest aligned with ours. In particular, they had the experience that we needed in online educational delivery. They had the experience in creating a product that was interesting to the students and captivated them. They had a particular platform that lined up with the sort of thing that we wanted to create. They had support for IP and a whole bunch of other things that you're probably not terribly interested in, but our lawyers cared quite a bit about. They were small. They were focused on doing 1 or 2 degree programs, 1 or 2 projects at a time, rather than to do hundreds. And they had experience, in particular Sebastian had experience on doing massive scale projects. For those of you who don't know, Sebastian Thrun, who's a roboticist, worked for Google for many times. He was the one who built the system that allowed for all the mapping of Google around the world, that built that organization together to do sort of rapid online manufacturing of maps. And so they had a lot of experience in doing this. We seem to have a nice little match. It does turn out that there are some differences between what a company wants out of something like education and what a university wants out of something like education, and I'll try to get to that towards the end. But by and large, our interests align. So this is what a course looks like from the point of view of the process of making a course happen. We have students, perhaps thousands of them, hundreds of them, dozens of them, how many. We bundle them together with what we're going to call course mentors, people who are able to work with them one-on-one, some of whom live with Udacity, the bulk of whom, for all the educational and academic content, live at Georgia Tech. They are themselves managed by quality specialists who are able to deal with issues as they sort of bubble up, and eventually it works its way to the instructor of record, the creator of the course, and the course developer. Importantly, the course creator and the instructor of record is always the same person when the course is first produced. And in fact, for all the courses that we've created so far, they remain the same person for all the semesters that we've been running the program to date. What's hidden inside of this chart is this notion of dealing with scale, of figuring out how to separate out the different kinds of questions and problems that students deal with. And I'll talk about that a little bit later. But here, you'll notice, different from what we normally see in a sort of MOOC-related course or a degree program, is lots and lots of human beings. So there are TAs, there are graders, there are large amounts of humans making up the infrastructure to make certain that the students can succeed, and this turns out to be crucial to the notion of whether this is actually going to scale. So how do we get to a $6,600 degree? How did we come up with a price like this? Well, we did something very simple. Well, not that simple, but it seemed simple at the time. We sat down over multiple Sundays, over multiple months, and we tried to figure out exactly how much it cost to do a degree per course. How much did it cost to create a course, to get the faculty involved, to get these instructors of record involved, to get all of the TAs, to do all of the things that we had to do. And it turns out that there are two basic costs. There are these fixed costs, creating a course, which, by the way, done the way that we do it, costs anywhere from $250,000 to $350,000 just to produce one of those courses, which is a lot of money, but it's a fixed cost. So you produce one of these courses once, and you're able to use it again and again, multiple times, perhaps over multiple years, only occasionally going back and updating it as things move along for sort of a fraction of the cost. So that $350,000, while being large, disappears over time. The real cost comes with scale. Those people that I showed in the chart before. If you have to have a TA or a grader for every 20 students, then very quickly you get overwhelmed by the cost of hiring the people. So we sat down, we worked out how much it would cost under certain mild assumptions of scale, that the fixed costs would go away and that we would be able to scale sublinearly with the number of students, and we ended up with something that amounts to about $6,600 if you do it over a 3-year period. It works out that the $2 million gift from AT&T happened to almost exactly, down to a few $100s, cover our costs for the first year. And so we do remain in the black, and it looks as if our initial cost estimates are right. It turns out, and I don't think I have to tell people who do software engineering, this is incredibly difficult to do, to actually cost out how much one course per 473 students, whatever really costs. But we were able to do it. We made some guesses, some of which we more or less made up on the spot, and it turned out we were relatively close. Now, in addition to the degree itself, it's worth, I think, for an audience of academics and people who've gone through university to just take a moment to describe how we got the OMS approved. For those of you who have been following MOOCs and the sort of online revolution, as it were, you'll know that it's quite controversial. It was also true at Georgia Tech that this was controversial. In September of last year, or year before, we met with Sebastian, decided that this is something that we wanted to pursue, and we took it to the faculty. We appointed a faculty working group so that a proposal would actually come with faculty buy-in. The college leadership was barred from the working group at their request, so that it was generated only from the faculty and not with any administrative oversight. They spent about 6 months going to the various departments in the College of Computing, going through various possibilities, listing the set of things that they wanted to have happen. And the proposal was brought before the faculty in the college, who voted to approve it 75% to 25%. It moved through the institute fairly quickly from there. If I had to summarize the concerns of the faculty, not just inside the college, but at the university level and even at our Board of Regents, it really boiled down to one thing: quality. Is it possible to create a degree program like this and still be able to produce quality students at the end? Will we attract quality students? Will we be able to keep quality students? Will we produce quality students? And that was their concern. Of course, the answer is it's an empirical question and you don't really know until you actually do it, but we did commit to doing our best to doing it and spending whatever money was necessary to make it happen. It is worth pointing out that if you work out all the math, we managed to do all this in about 7 or 8 months, which for people in universities, you know that's an amazingly quick time to do anything. It turned out that we were lucky. It turned out that purely coincidentally, about 2 years prior, we had gotten approved through the Board of Regents and through the Institute the notion of an online degree. Georgia Tech has 6 of those. They're very different from this approach, but because we had already done this, we didn't have to go through the entire process again and get approvals all the way up the chain and all the pre-proposals and all the other bureaucratic red tape that you have to go through. And if we had, I would be having this conversation at ICSE 2015 because it would have taken another year to go through. So in some ways we were lucky that we were able to do this, but also we were lucky that we had a set of faculty who were interested in trying to figure out whether this was going to work. So in fact, you might ask the question, why would the faculty care about this? What's in it for the faculty? There are a lot of possibilities. You'd have to ask them yourself, although I'm one of the faculty members teaching one of the courses. But it did turn out that before we went through this entire process, we had about a dozen faculty volunteer to participate in the degree program and to teach their courses. When you asked them why, they gave different reasons, but they basically boiled down to simply improving teaching and improving learning. Many of them had wanted to experiment with the notion of flipped classrooms, with figuring out how to get their material in some place that was interesting, and be able to take the time in the classroom to work on projects and to do one-on-one mentoring, and thought that this might be an opportunity to do it, even if the OMS itself did not fly. It gave them a lot of opportunities to rethink pedagogy, to think perhaps for the first time about their courses in any very serious way for over a decade. I teach the machine learning course. I've been teaching it for 12 years now. This is the first time I really sat down and really thought about how I was presenting the material and how I would have to do it differently. And the course benefited, the on-campus version of the course benefited from it. And many of the faculty, I think, wanted to have that experience. Another thing which can't be underestimated is simply fame. You have the possibility of reaching not just 200 students a year, but 200,000. To educate hundreds of thousands of people and to have them go out and spread the gospel of Alex Orso or Charles Isbell. And for a lot of faculty, that was an intriguing possibility. We had one faculty member noted that in the one time he offered his course, he had managed to reach more women computer scientists than he had in the previous 15 years, because there were that many who were participating. And this is something that is both selfish but also altruistic. The idea that you can actually reach out and touch that many people and have that kind of impact on the way that people think. But despite the fact that people were volunteering to do this, we decided we needed to pay them, and so we did pay them. You can ask me about the details if you're really interested, but at the end of the day, we pay them a fixed amount of money for creating a course, a fixed amount of money for being the instructor of record, whether or not they created the course, and a fixed amount of money every single semester that the course is offered, whether they're engaged in it or not. You may think of it as a royalty. It is not a royalty, because that's a legal term that has consequences, and I'm required to look into the camera and say, under no circumstances do we pay royalties to our faculty. That would be a legal officer. However, you can think about it if you want to as if it's a royalty. It's roughly $2,500 every time the course is offered. It turns out that the amount of money that the faculty came up with as a proposal, the amount of money that we came up with as a proposal happened to align. And it works out to be roughly the same as saying that creating a course is the same as teaching an on-campus course. Teaching one of these courses is worth roughly half of teaching an on-campus course, and then there's a small fixed amount of money for reuse of the material. There are many people I've talked to, my counterparts in various other universities, who try to do similar things, and we seem to have all independently come up with the same model. So there's some hope that if we move, as we move from a kind of consulting view of this, something that's in addition to what we normally do as faculty, and start thinking of it as being integrated in our normal workload, that we have a model that everyone seems to have come to together that sort of makes sense. Some way of measuring the amount of work that's required by individual faculty to make this happen. So that's how we got from here to there. But now we're in the middle of the process. So what happened when we actually announced this to the world and we released it out there? We had an application period of 3 weeks. During those 3 weeks, we got 2,361 applicants. That's about twice the number that we get for our on-campus MSCS. Those applications came from 77 countries and represented all 50 states in the United States. The vast majority of the applicants were degree holders who were already working in computer science and IT-related fields. And 85% of those applicants were US citizens or permanent residents. To put that in some perspective, for our on-campus Master's of Science in Computer Science, 85% of the applicants are foreign nationals. The vast majority of whom, by the way, are from India, followed a very distant second by China and a few other places around the world. Now, of those 85% of people who are in the United States, as I said, the vast majority of them were already working. They're about 11 years older than our on-campus MSCS applicant counterparts. So this implies that we actually found a new market. There are people out there who want to get advanced education, who want to get their master's degrees, either because they just want to learn or because they want to move up in their companies, and they simply weren't finding it feasible to do before. Here was an opportunity for very little money to get a Master's of Science program from the #9 ranked computer science department in the United States. And they took it, or at least many of them took the opportunity. Now, of course, you might ask, why aren't these people just taking a year or so off from their jobs and going and getting a master's degree? Well, they can't, right? They've got a job. They probably have kids. They have mortgages. They're not going to move from California to Atlanta, which, although Atlanta, by the way, is a beautiful city and I encourage all of you to visit, most people who've never been in the South have this notion of the southern United States, which is suboptimal, let us say, compared to what it really is. It isn't. The South is a beautiful place. Atlanta is the world's largest urban forest. It's beautiful. But not a lot of people know that, and a lot of people aren't willing to uproot their lives to get a master's degree for the possibility of moving forward. But if they can do it in their own homes, the comfort of their own homes, and they could do it for $6,700, then maybe they'll be willing to do it. A couple of other things worth mentioning. We admitted about 400 people from the initial 2,400 or so. We did not deny the other 2,000. We simply didn't admit them for the first semester. We chose not to admit them for the first semester because we wanted to keep it small, wanted to make certain that if anything bad happened that we could handle it. That's roughly the number of people that we would admit to our Master's of Science program on campus, and so we knew we could handle it if something went wrong. And so at least for the first semester or two, we wanted to be small, we wanted to be careful, we wanted to take our time to do it. So we admitted these people. The vast majority of them accepted. We got something like a 98% yield rate, and we moved forward. I want to mention one thing before moving on, which is, for reasons we don't entirely understand, the gender distribution of our initial applicant pool in our first class was more male than our on-campus. It's actually lower by a few percentage points than what we would have expected if we assumed roughly the same kind of demographic distribution. It turns out we have no way of knowing whether we're doing well or whether we're doing poorly, because Google aside, who just did this for the first time last week, most of the large companies where we're drawing this population do not release statistics, demographic statistics on their working population. So we might be doing exceptionally well. We might be doing much better than the base case, or we might be doing terribly. In either case, we're trying to figure that out, and I'll mention at the very end some research projects that we're doing to kind of understand what this means. So, here are the first set of courses that we did. Starting in January, we created 5 courses. They're listed up there, everything from operating systems and networks to software development, machine learning, and artificial intelligence for robots. You will notice that of the 6 people who are up there, 2 of them are not Georgia Tech faculty. So on your left, the very bottom is Sebastian Thrun, who's the founder of Udacity. He teaches the artificial intelligence robotics course. He is now an adjunct. And to your bottom right is Michael Littman, who is a world-renowned machine learning researcher and is a good friend of mine, and we co-taught the machine learning class. I'll give you a couple of examples of sort of how that works in a moment. In the upper right is Alex Orso. I will give a couple of examples from his class in just a second. Software engineering, by the way, is one of the best well-received of the courses that we did. It was one of the ones that was most requested by potential students, coming second only to machine learning, which is the class that I teach. So what's really interesting about the MOOC platform and with this set of courses is the diversity that it represents in approaches and ability to convey content to students. So I'm going to show an example of how Alex conducts his course, and I'm going to show an example of how Michael and I conduct our course, and I want you to see some of the differences in the way that we interact to sort of give you an idea of some of the potential that's there. So we're going to see if this works.
So we're going to start with the course overview. In this course, we will cover several aspects of software engineering. We will discuss the concept of software process and study different types of processes from rigid to more agile. We will also look at the different activities or phases in the software development process, and we will look at those in detail. Throughout the class, we will also learn how to use modern tools that can help improve programmers' productivity. Finally, we will put what we learn into practice through a set of realistic projects of increasing complexity. So now let me quickly go over the course structure. The course is divided into 4 courses, just like this cake is divided in 4 main parts, in 4 slices. Each course has a main topic and a project related to that topic. Specifically, the first mini course introduces software engineering and presents its basic concepts, including the different software phases and the different types of development processes. The other 3 courses focus on a specific activity within software development.
So, by the way, we polled our students and asked them what they thought of our classes, and Dr. Orso's class won for best graphics. So, which you can see, it's a beautiful, beautiful piece of cake. It is very well received and is the most popular course being taught this summer. What you'll see, yeah, Alex. I highly encourage you to hunt down Alex. He's sitting over there, and ask him how he put his class together and sort of how he feels about it. But one thing I want you to see, a couple of things I want you to see from this particular snippet. Notice that you see his hand. There's some cute little tricks with planes and the hand being over whatever's going on. This is kind of the Udacity way. There's not a focus on his face, although he does have interviews. He does have snippets of video where he's talking directly to the students, but typically this is the experience that students have. In addition to seeing this, there's quizzes that you interact with every 5 or 10 minutes or so. There's a quiz that asks you to go back to what you've just experienced, answer some question, but you have to answer correctly before you can move on, and this is more or less the experience that students get. Now I want to contrast that with what Michael and I chose to do. So Michael and I, like I said, are really good friends. We've known each other forever. We both do machine learning and have been doing machine learning for the last 20 years, but we actually have different views of the way that machine learning should be taught and different views of the way that what's important inside of machine learning. So what we decided to do was to do a little experiment. We set him up at the studio in Providence, Rhode Island. He's a professor at Brown. And I was in Atlanta. And we would get together at the same time, him there, me in Atlanta, and we would simply teach each other. So at one point, I would be the teacher, and he would be the student. At a different time, he would be the teacher, and I would be the student. The teacher would prepare, would figure out exactly what they wanted to cover, figure out what the quizzes were going to be to present, and the student would not prepare. So it's just like the on-campus experience. And the student would sit and listen, and he would ask questions, interrupt, and try to drive the conversation in the way that he wanted it to be driven. So the idea was to create a kind of podcast and a way of doing interaction from two experts in the field acting as a proxy for the student. And so we ended up with something that looks like this. Oh, or I could start over and I could do it with actual audio. Hi, I'm a Mac.
No!
All right, we'll start over. Let's do this right.
So when I wrote these down, I started to think, boy, they're more different than you'd expect just by sticking an "un" in front.
How so?
Well, they don't seem to really, the definitions don't seem to have all that much in common. You know, it's not like this one uses label training data to generalize labels to new instances, and this one uses unlabeled training data to generalize labels to new instances. Like, I would think that you'd have the definition of one, you just stick an extra "un" in there.
Well, that's kind of true, right? So if you do some data description and make sense out of unlabeled data, and then I give you a new piece of data, somehow using that description, you would know how to describe it.
Maybe. I mean, there's definitely some unsupervised learning algorithms that do some amount of generalization, but it's not as unified. I think in some sense, the concern here is that unsupervised learning is just not as unified a problem or as well defined or crisply defined a problem as supervised learning is.
Oh, I think that's definitely true. Here's the game. You got two people. These two people are criminals.
Oh no! Are they smooth criminals?
One of them is.
So what I want you to get from that is that the way we taught this class is we talk to each other. We interact with one another. We're good friends. We go back. We have the same sense of humor, and we sort of interact with one another. And this went on for many lessons. It was a lot of fun for us, but it turns out it was actually fun for the students as well. And in fact, the feedback that we've gotten has been overwhelmingly positive, both for all the courses in general and for that one in particular, and for each of the courses, but for very different reasons. So one of the things that we were worried about when we created these courses and we created this degree program was that the different approaches would be, and creativity would be squeezed out by the production process. But it turned out that rather than squeezing it out, it actually opened up possibilities. Michael and I, we've always wanted to do something like this. It simply would be impossible to do it every semester. Now we have a way of doing it together and arguing back and forth about the right way of doing something. The same is true for each of the other courses. So I'm just going to show you a couple examples of feedback that we've gotten from students. This is all public information. It's on Facebook and Google+, so I haven't violated anyone's privacy rights by showing this. This particular guy happened to have taken the software engineering and the machine learning courses. He loves it. He talks and talks and talks about it. I'll show you a graph in a moment that I think really brings this home. We worked really hard to create a sense of community. So we gave all of our students t-shirts, everyone who was accepted. And this is a picture of one of them posting on Facebook about it. Every time we have new students who apply and we accept them, we send them these t-shirts. Also worth pointing out that the students talk to each other. They're trying to build a notion of community. This turns out to be incredibly important to the success of students as far as we can tell, and to their engagement in the process. For example, they're working together a meetup. They're going to come to Atlanta in the fall for our homecoming game. Looks like somewhere between 80 to 100 of them are going to try to find their way to Atlanta to come to a football game because they want to be a part of, in this case, the Georgia Tech experience. So this notion of interaction turns out to be central, one of the lessons that we've learned, which I'll get to in a moment, but I want to show you this graph by way of preview. So I taught, in fact, by coincidence, for each of the classes that were taught this past spring, there was also an on-campus version that was taught. I taught both the graduate version and the undergraduate version of machine learning. The undergraduate version is the line in red, and the graduate version is the line in blue. This graph on the x-axis is the number of students who have generated an interaction sorted from least to most, and the y-axis is the cumulative number of interactions. Okay, so it should go up. If you look at it, you'll see that it obeys a power law. Both of them do. But the other thing that you'll notice that there's roughly twice as many students in the undergraduate version of the class. I had somewhere between 150 to 200 students when I started off anyway. So there's almost twice as many people on campus as there are online, but you'll notice that the total number of interactions for the online is 8 times as much as the number of interactions for the on-campus students. All of the students were interacting constantly, trying to talk to each other, not just, it turns out, about the class, but largely about the program and all kinds of issues that sort of brought them together. A lot of complaining, a lot of kibitzing about the way the class could be better, about how their interactions, questions about, but mostly to each other and less to the TAs and less to me. So that's a ridiculously huge difference in two otherwise exponential curves, and I think that it comes to something very central about why this program will succeed or why this program will not succeed. So here are the lessons that we've learned so far going through this, and again, you'll see that this notion of community is central. It turns out, first off, it's not difficult to create a quality product. I mean, it's hard in the sense that it requires work, but it's not hard in the sense that it requires coming up with something completely new. It's not as difficult as getting software engineers to communicate with one another, for example. It really is as simple as sitting down, working through your class, working out what the learning objectives are, and simply putting them together. The scalability question, which is central to whether we can pull this off or not, it turns out that it's easy, except, of course, the parts that are hard. The parts that are easy are, for example, it turns out I only need 1 TA. It doesn't matter whether I have 100 students or I have 1,000 students. And in fact, the number of unique questions that we get, or the number of questions does scale linearly with the number of students, but the number of unique questions remains a constant. So if you have someone who's dedicated, who's looking at the forums, who's interacting with the students, and being able to broadcast out as well as to take in, it turns out you don't need to scale the number of people answering questions linearly with the number of students. What does scale linearly with the number of students is the number of graders. The fundamental question we have yet to answer, but we must answer in the next few years, is how are we going to grade and assess the students in a way that we feel comfortable, they feel comfortable, and their potential employers feel comfortable without having to hire 1 grader for every 50 or 100 students. Because if we have to do that, then the costs scale linearly, and it's difficult for this to break even. But that's okay. We've been thinking about how to figure that out, and we have some ideas about how we might do that. I'm happy to talk about them offline. The other thing that matters here, and why I showed you the slides before, is that this notion of community matters a lot to the students. In fact, we believe that this notion of community is what's going to lead to the individual students, all of whom are vastly qualified. They're easily as qualified as our on-campus students by sort of every measure that you would come up with. But in order to succeed, they have to be able to work with other people. They have to be able to coordinate. They have to be able to ask each other questions. And technological support for community building, not just communication, we think is crucial for making this happen. The students are extremely engaged, both officially and unofficially. As I showed before, they're trying to do this meetup in Atlanta. They've created their own Facebook page, their own Google Plus page, their own IPC chat channel. They've created all of these ways of interacting and talking with one another, and they're all very active in it. They provide a significant amount of peer support. And something that I think is worth pointing out here, and something that I sort of knew was true going in, but I was sort of struck by as the process went on, is that what they really care about is not the course, not how to download this piece of software. What they're really interested in is the degree. Their questions are all about, what's the next class I should take if I want to do this? They're asking advisor questions, why you have professional advisors. They want to know, if I take these 7 courses, will I graduate? Does this fulfill this particular specialization? Those kinds of questions. So one of the things that it's a challenge for us, and something that's important in a degree program, is we have to figure out how to take our incredibly good advising process that works on campus and make it work here in a way that's also going to scale. And that's still an open question for us, but we think we have a handle on at least how to make that happen. And regardless, we're going to have to figure out how to do it, because that's the thing that the students need in order to succeed. The last thing I just want to mention here on the lessons learned so far is that expectation settings seem to be the crucial, important thing that perhaps we didn't do as good a job of as we should have. A lot of the students come in thinking that, oh, this is just going to be like this MOOC that I took for 7 weeks sometime, and then they discover that it's not. So a concrete example of this is we decided for the first set of students, for a bunch of reasons, to limit them to only taking 2 courses. We got literally hundreds of emails from students complaining bitterly that we would only allow them to take 2 courses. They wanted to take 3, they wanted to take 4, they wanted to get through the program as quickly as they could. 3 or 4 weeks into the program, we got dozens and dozens of emails from students thanking us for not letting them take more than 2 courses. The workload was too high, they've got jobs, It turns out that it's very difficult to take Alex's software engineering course and to do your job and to raise your kids and to do all the other things that you have to do. And so many of them, including the ones that took 2 courses, dropped down to 1 course. Vast majority of them made it through just fine, but they had to rethink their expectations. There's a separate part of this sort of expectation setting that is different from the workload and really just has to do with how the students view this. You don't have to read this, although this is a cartoon that I put on my webpage explaining to students what my teaching philosophy is. Students see this in general, but specifically for online courses, as a service economy issue. They're paying my salary, which they're not, and they demand my time, which they're not going to get if I don't want to give it to them, and they demand that whenever they have an issue that I respond to it and that I change everything about the way machine learning is being taught in order to accommodate their needs or whatever it is they think ought to be. But of course, we're not living in the service economy, we're living in the information economy, and my job as a professor is to leave them less ignorant. It is not to make them more happy, right? And the students, many of them came in, they're 35 years old, they've been out there in the world, they're used to seeing themselves as sort of customer-focused people. They see this experience, at least many of them came in seeing this experience as if it was more like an executive MBA. That I'm paying for a service, and you should make it easy for me to get through, as opposed to what we do at Georgia Tech, which is about anything other than make it easy for you to get through. They eventually adjusted to that, or are adjusting to it, but setting that expectation properly before they walk through the door is incredibly important both for their happiness and for their abilities to succeed. So, what's next? So we're in the middle of the next application period. For the year, we have somewhere on the order of about 4,000 applications. It looks as if the vast majority of them are, in fact, qualified students. We're expecting to have about 2,000 students in the program at the end of December, starting in January. We are creating additional credentialing tracks. We have a non-credit certificate and courses that we are experimenting with right now as a different path for going through this program. Rather than getting a degree, you take 1 course or 2 courses or 3 courses. We give you a certificate. It's a different experience. It's not the same as a degree. It doesn't give you credit. You can't transfer it into our program or to anyone else's program, but it does satisfy the need of it does satisfy the need of people, for example, who are working full-time and want to learn about data mining or the latest cutting-edge theory in software engineering. There are some ideas here that might help us to manage the scaling issue. For example, if it turns out that there's an order, which we believe there's an order of magnitude more people interested in this sort of professional certificate, we can use some of the money that they give us in order to support our online master's students and to deal with that problem of scale by at least dividing the constant by an order of magnitude or so. And there are a bunch of other things that are going on. One that I'll mention is collaborations with entities that are out there. Our partnership with AT&T has been fruitful in the sense that they gave us money and it helped them because their students, their employees applied in large numbers and many of them got in and were able to do something that worked for them as individuals. By the way, let me just mention that somewhat to my surprise, the 77% of the people who applied for this program who were already working at a large company of some sort claimed that they planned to pay for it themselves rather than ask their company to pay for it. Because they wanted to get through the program. It's just inexpensive enough over a 2 or 3 year period that they felt they could get this degree and they wouldn't owe their company anything. And that was more powerful and portable for them. So we've been collaborating with universities. One of the things that I spend my time doing is traveling. I went to Africa in November. I'm going back to Africa in a couple of weeks. And we're trying to find partners in places like that, where there are people who are interested in doing the capacity building, who are capable of getting not just a Master's of Science, Computer Science, but simply can't find it within their means, either because it's too expensive, it requires leaving the country, or in other ways requires too much time. And we're working with organizations there, including a large multinational that I'm not allowed to mention right now, who are figuring out ways to hire these students, assuming they meet their standards, to pay them to work with them on projects while they are getting their master's degree online with us. This is a big win for the students, it's a win for us, and it's a win for the companies. And in particular, it's a win for the students because it gives them a place where they can build this community locally and interact with 10 or 20 or 50 or 100 other people going through the same process they're going through in the same way that they're going through, with the same background that we're going through. And we believe that that sort of thing is necessary in order to ensure the success of students who otherwise certainly are capable of going through the degree. So, concluding thoughts. This is uncharted territory. Not anyone else has done quite what we're trying to do, though people are beginning to do so. We've had an overwhelming reaction, both positive and negative, though mostly positive. There's been over 600 unique newspaper articles about this. There's a lot of people paying attention. I get invited to software engineering conferences to give talks about it, for example. We think this is a tremendous opportunity to offer advanced education throughout the world, and something that's going to work not just for us, but work for everyone else that is out there. There are a number of issues around collaboration, around students interacting with one another, and around pedagogy and education that are finally that we finally sort of have an excuse to think hard about, including, in reference to the opening talk, data mining. There's a number of sort of data mining approaches that we're applying to figuring out when students are lost, when they need help, how well they're doing. I have a dashboard that is given to me when I teach my course that lets me know which students seem to be falling behind and perhaps why, and which ones are seeing weight or going over quizzes over and over again. There's a lot of information that's available, some of which can be not only automatically gathered, but there can be automatic intervention for. There's a lot of wonderful sort of possibilities here. And I don't know where it's all going, but I do think I know when we're going to succeed. I think we will succeed, one, when the rest of the world thinks we've succeeded, when we have courses that are shown to be top quality, which I believe we have created, and that we're able to support scale, and that we've got 10,000 students, and that they're happy, or at least as happy as our on-campus students are with their experience. When those people are hired, when they go out in the world, and people just see this as just another way of getting an advanced degree, we've managed financial viability, and others start to follow. So in that vein, we have launched a number of research programs. I won't go into them in detail, with various partners, at least around the US, to kind of try to understand better how we're going to make this work. And so with that, I think I will end the talk and open it up to any questions that you might have. Did not mean to do that, sorry. Yes?
Thanks for the very interesting talk. My question is, how is this going to affect or change also on-campus teaching?
So there are two answers to that question. One is we don't know yet, but so far the major difference seems to be that it's given people the ability to really do that sort of flipped classroom thing. So we have many of the, well, not many of them, but many of the faculty who've started this process are now using this material. Some of them started in January. Students, you have to go see this. You get to see the same thing as the online students do. And then when you come to class, do you have any questions? We're gonna do it. It's sort of a problem-based learning. So people seem to be taking advantage of that. I did not do that because it was just too much for me to do the first semester. But now that I have the material out there and I kind of understand how it works, I plan on doing it next spring when I teach the on-campus. Alex, did you do any flipped classroom stuff? Right, so Alex said he did a little bit of the flipped classroom for a few of the lessons, but mostly stuck to doing the normal thing. You're expecting to do more flipped classroom things over time? Yeah, so I think that that's going to be one of the changes, other than just the fundamental change of rethinking the courses for the first time in a while. Yes?
So, one of the issues is as you scale up, the grading and plagiarism among the students and the grade expectation among the students. How is it that addressed?
Which expectation?
Grading expectation.
Grading expectation.
I expect A grade, but I got a B grade, and there is plagiarism among the students who are collaborating elsewhere. How do you check for all those things? That load is going to be pretty much high.
So there's a bunch of questions there, if I understood you correctly, really about grade expectation. I think, so I'll try answering a few of them. I think that well, first off, this is a problem on campus too, right? So there's really nothing new there.
But the scale will be much higher.
But the scale will be much higher. That's a fine point. There's a sort of fundamental question. This is one of the questions that always gets asked of how do you verify a student is who a student is, for example. Right. So for testing, we know how to do that. We use an online system whose name I'm blanking on right now, ProctorU, which, so when a student took my exams, I had 2 exams. When a student took my exam, he or she had to sit down in front of their computer, could only use Windows or Mac, could not use Linux. They gave up complete control of their machine. There was a person on the other end watching them. as they took the exam and could tell which applications were being run, not being run. We were very specific about which things they could run, which things they couldn't run, where their internet connection could go. They had to show 2 forms of ID to prove who they were, and when they finished the test, it was uploaded, and they had to delete any side material that they had, and the person watching could determine whether that was what was happening. So that helped with testing. And I feel fairly confident that the vast majority of the people, well, first off, most of the people doing this, we haven't yet gotten to 10,000 students, 9,000 of whom just want the degree. We have relatively dedicated older people who are trying to actually learn something. And so I don't yet think that's that big of a problem. Having said that, we have had one case of possible academic misconduct, which was easy to catch. And we're going through that process now, so I can't really talk about it. But yeah, it's an issue. As far as projects are concerned, no, we don't have an easy way of doing that, though we could impose these kinds of requirements on students if we wanted to. I will point out that, you know, that's a problem on campus as well. Yes?
A related question. Here is a setup I have. I have a machine. I have 2 keyboards connected. And I am sitting in front of the machine and the monitor, and you are seeing me.
Yeah.
My friend is sitting next to me. You can't see him because the
no.
camera doesn't
The first
cover.
thing you do is you take your computer and you move it around the room. They can see everything in your room.
Yeah, but he comes after that.
Yeah. So,
So what I'm saying is, see, you mentioned one particular thing, that does it not happen in real classes? It does not happen in the final exams. It can happen a bit if you are slightly careless in assignments, but in the final exam, we are at least assured that people are sitting separate, they are not copying from each other. So that's one thing that I agree, this is starting, but that's something you have to take care of.
So the observation is, well, one version of that observation is, if people really, really want to cheat, they will find a way, which is true. I don't think that they'll be able to hide, you know, just outside of the view of the camera and you get answers from them because they can't see the screen. I think that would be very difficult. But I agree that people who really, really want to will find a way to cheat, and we will catch them because it's usually really easy to do. Anyone who's taught a class knows it's not that hard to find the people who are cheating. The real question is whether you want to go through the effort. So I'm not particularly worried about that case, but I do agree that it's, you know, a sort of fundamental question. But I do think, if I can take a step back for a moment here, that insofar as those sorts of concerns are legitimate, including ones about the quality of the courses, whether you're actually meeting your learning objectives and all the other things one might come up with. Insofar as that is true for our online courses, it is also true for our on-campus courses, and that it is wrong to focus on one without focusing on the other. Not that I'm accusing anyone of doing that. But if you find yourself asking questions like, well, how do you know this course is as good? Then you should ask yourself the question, how do I know my on-campus course is any good at all? And the truth is, for most of us, the answer is we don't know. We just go in assuming it, and that there's no real oversight, nor would you want that oversight of your fellow faculty members staring over your shoulder, making certain that you're actually teaching the course the way that they think the course ought to be taught. Most of you would be extremely upset about that. So these questions are legitimate, and I welcome them, and I think we should all ask those questions, but I also think they have implications for on-campus, and that's actually a good thing, but it is a thing that has implications for the way that we do business overall. So yes, and then yes.
Hi, so I really appreciate the noble idea of broadcasting knowledge to more and more students. But like I have 2 questions. I'll maybe start with the first one and then wait for the second. My first question is that, so can you throw some light on the accessibility to softwares and hardware resources to the off-campus MOOC students, and how to maintain the increasing load on these resources because of the MOOC students?
Right, so if I understood your question, it was, there's a weird echo up here, which is why I may repeat some of your questions. There's a question of resources. So our on-campus students use a bunch of resources. If we now have 2 orders of magnitude more students online and we want them to have the same experience, they're going to have to use those resources. How do we make that work? Is that a fair characterization?
Yeah.
So the answer is, yeah, that's a problem. But it turns out that at least for most of our courses, except for a few specialty courses, we require that the students bring their own laptops. Almost everything that we use is available publicly in one way or the other. There are some exceptions. For those exceptions, in fact, the best example for that is advanced operating systems, which it was a very real concern how we're going to make that work, because they need to do all these special timing things on real hardware. The Udacity folks who have the ability to hire an enormous number of engineers to come in and think about problems, came in, worked with Kishore Ramachandran, and worked out a way to get the pedagogical outcome he wanted by using other machines, including their partners at Amazon, so that they could do the same kind of low-level timings that they wanted to do. So these things are important questions. Mostly they're solvable, I think, by and large.
But sir, like there are many prestigious resources, we can say, like supercomputers and big clusters that a university might be having. Once you increase the number of students who are going to access these resources, the load will be very difficult to manage.
Sure.
Isn't that the case?
But you know what the truth is? For most of the stuff that we're asking these people to do, even for advanced courses, Amazon's got more computer power than anybody. I mean, it doesn't matter what we come up with, and that we can usually find ways to solve those problems. And by the way, it's bursty. So it's only this 3-week period where we need this. So you can be very clever about scheduling and sort of make it work. Are we out of time? Is that where you're looking at me? All right, one last question. I had said you, sorry.
Hi, Charles. I enjoyed your presentation, and I'm encouraged. I've taught online for about 9 years total before. In the last few years, I've been at Rose-Hulman, where we don't teach online. Of course, I've been trying to encourage people to take a look at how to use online resources in our teaching. One of the things that comes to mind is when I teach online, I take twice as much time to prepare as I do for something that I would do in an ordinary classroom. They're just things that you have to accommodate. And then, of course, in the teaching, after teaching, you're going to always have the questions, and not all questions are created equal, and you don't know that from the question that's coming because you don't have the interaction with people. So there are things that you have to accommodate, and I was encouraged that you give extra resources and for that matter, financial resources, let's say a motivation to the professors to teach, or the instructors to teach the online courses. Of course, the first thing that came up when I tried to bring up the idea of online at Rose was, okay, you're going to be siphoning off of existing resources in order to make this other program work. And at first I thought they just meant faculty. Okay, and it's true, whenever you start something, you have always got to siphon something off the existing folks to get things going. Okay, so that's an accepted, let's say, bump at the beginning. But the one that came to me that I'm going to ask you about now is you siphon off of department resources, things like the distraction that it creates. And the second one was the prestige, and you brought up the prestige earlier. I'm really glad when you said in your course, or your courses, this is not an easy course. So you don't get the University of Phoenix effect, if you will. Now, why I'm encouraged by that is because you have a very good prestige. Now, how do you answer the question to your faculty, and for that matter, to your administration, about siphoning off of the resource that's called the Georgia Tech Prestige?
Right. So I'll give a quick answer to that. There are two questions there. One has to do with resources that are tangible, and one has to do like time. Time is, you know what I mean. And the other is things like prestige. So for the first, we got $2 million from AT&T. No quid pro quo, because then it wouldn't be a gift, but that managed to cover our cost. We have a special deal with the Institute where we get a large percentage of the money that we generate back. So we're like a startup inside the university. All the resources for this program have to be separate and apart from the normal budgeting process, and so eventually it must become sustainable, or otherwise we'll honestly just have to shut it down. There's just no way to make that work. On the prestige question, my claim is I can't answer that for at least 5 more years. The people who come out of the program will be proven in the marketplace. People will say, you know what? Those students are just as good as the students who come through the on-campus one. Georgia Tech's still a great place. It still makes its students suffer enough that I can hire them, and that's where it's going to have to go. And I think that's really the only answer to the question. It's an empirical question. I happen to believe, based on a semester and a half of experience, that we're going to get good enough students, we have good enough faculty like Alex, and that the students coming out of the end, they're suffering at least as much as our on-campus one, and that seems to be a part of the magic of getting a Georgia Tech degree, and so that they're going to be okay. We shall see, as the number of students we admit, the demographics of the number of students that we admit changes dramatically over time. But I don't think we'll know the answer to that for 5, 6, 7, 8 years.
Thank you. It sounds a lot like a lean startup, but it's an interesting.
Thank you. We have to stop now, so I would like to give a round of applause to our keynote speakers. Oh, a gift. Thank you very much for a very inspiring keynote address. Thank you.
Thank you, I appreciate it. Should do this more often.
I've been asked to remind all of you that there are poster sessions across the hall and vendors' booth that you are encouraged to go see and visit. Thank you.